In friction welding process, what we do, we take one workpiece on a clamp and another workpiece on a rotating spindle, and then we bring these two workpieces close to each other. One workpiece is held rigidly while the other workpiece is rotated at very high speed. Then you apply the axial thrust between them, which causes the generation frictional force or the friction between these two surfaces, and due to the frictional heat the material goes into the semi-plastic or deformed condition, and then with the application of this axial pressure the welding takes place. And in ultrasonic welding process, so ultrasonic welding process is mainly adopted to join the plastics and the polymer based composites. Sometimes it is also used to join thin metallic workpieces. One workpiece is placed at the bottom while the other workpiece is made to vibrate on its surface. The vibrations are of very small amplitude and very high frequency. The order of the frequency is of 20 to 25 kilohertz. Axial pressure is also applied simultaneously. Due to the vibration between them, frictional heat is generated, and then it causes the localized melting and the joining of the workpiece together. Then we have this induction welding process. It works on the principle of induction. The workpieces to be joined are passed through an induction coil. It causes the setting up of the eddy current in a localized zone, and then you are applying the axial thrust between them, which causes the formation of the bond in the localized region. The heating caused by the eddy current or by the induction phenomena causes the melting of the workpiece. This pressure applying in the axial direction causes the formation of a permanent bond. So this is the brief introduction about the pressure welding process. If you want to study more, then you have to refer some books. Let's come to some advanced topics of this process. In a typical fusion welding joint, the filler metal has been added, which consists of several zones. When you add filler material between the parts to be joined, or sometimes it's a case of autogeneous weld when there is no additional filler wire and the workpieces to be joined are very thin, but the localized heat causes the formation of three different zones. One is the fusion zone, where the fusion of filler material and the weld base metal takes place by the localized heating or localized melting of the workpieces. And then we have the weld interface, which is formed between the fusion zone and the base metal. This third zone is your heat affected zone, which is the portion of your base metal which has been affected by the applied heat during the welding process. And then rest of the material is the unaffected base metal zone. So this is the diagram which shows the typical diagram of a weldment, which has four distinguished areas. One is the fusion zone, other is the fusion boundary or fusion weld interface, and then third one is your heat affected zone, and fourth one is unaffected base metal zone. This is the macro graph of a cross-sectional welded joint. These sheets were very thick, so intentionally you had to create the V groove between them, and V groove, which is called the beveling. The correct term is known as the beveling of the edges. So you make them beveled, and then you bring these two workpieces together, and with the help of your filler wire or the electrode, which is consumable in nature, you supply the weld metal into this particular welded zone, and the fusion has taken place in very small region here, which is known as the weld interface or the weld boundary. You can see this particular portion is the portion of heat affected zone, which has undergone the thermal cycling during the welding process. This particular portion is known as the root of the welded joint. During the welding, the heat input can be calculated by this correlation, which is Q equals to U into I into 60 over V into 1000 multiplied by the efficiency of the welding process. Q is the heat input kilojoule per millimeter, U is your applied voltage, and I is the current, and then this divided by V welding speed, which is in millimeter per minute. You have the heat input in kilojoule per minute, and then you have to multiply by this formula with the efficiency. This is called the thermal efficiency of a welding process, and it depends upon the type of welding process to be used, because all welding process are not efficiently same, and they have different efficiency that depends upon the type of the power supply used, welding transformer, power source, and the method in which you have protected your weld pool. So all these parameters affects the efficiency of a particular welding process. In manual metal arc welding process, the maximum efficiency you can reach is 75%. In MIG and MAG, you can reach up to 90%. In submerged arc welding, as I told you, that whole of the process is taking place under the submerged condition, and there is a complete covering of the weld pool and the arc. So maximum amount of heat is supplied into the welded joint, and then we have the TIG. So these efficiency are in very ideal conditions. However, in case of this TIG welding process, in most of the books or in the engineering research paper, you can observe it maximum up to 60%. So similarly, in submerged welding, you can reach up to 80%. In MIG welding, MAG welding, in MIG welding, you reach up to 70%, or in manual metal arc welding, this is also very less, reach up to 50 to 60%. So these are the efficiency which have been calculated under very ideal conditions or with the help of some correlations. But in actual welding conditions, this is very, very difficult to achieve this much efficiency. This is my brief discussion about the formation of the weld and the different welding zones observed in the welded joint. If you like the video, please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.